March 1st, 2017. Something that I see ignored a lot in a lot of the papers that I read, a lot of the documents that I review and online articles and whatnot, is the presence of carbon. I have here the Elements book. This is a really cool book. I suggest buying it if you want to look it over, look for clues. But carbon is very versatile. I'll go ahead and read this out. Little story time for you. Carbon is the most important element of life, period. Sure, there are many others without which life would not exist, but from the spiral backbone of DNA to the intricate rings and streamers of the steroids and proteins, carbon is the element whose unique properties tie it all together. The very term organic compound refers exclusively to chemicals containing carbon. Not content to be the foundation of all life, not content to be the foundation of all life on Earth, carbon also forms diamond, the hardest known substance, at least for now. Challengers are discussed under boron, element 5. But contrary to popular belief, diamonds are not particularly rare, nor are they unusually beautiful, nor are they forever. All three are myths created by the De Beers Diamond Company. Diamonds would cost 1/10 as much, but for De Beers monopoly control. Cubic zirconia or crystalline silicon carbide are just as pretty, and at high enough temperatures, diamonds burn up into nothing but carbon dioxide. For those that don't know, look up moissanite. Moissanite can fool diamond testers very well, and it has a higher refractive index. So if you have somebody in your life that you want to buy something really pretty for, that shines more brilliantly than diamond does, look up moissanite. It has a hardness of 9.5. It's not actually a 10, but its refractive index is a lot higher, which means it is more brilliant when you have white light shining through it. But basically, that's that in a nutshell. It's element number 6 on the periodic table. And the main reason why I wanted to discuss this is it's very versatile, and it has a role in the formation of life during stellar evolution. And in this theory, stellar metamorphosis, it has a role in the formation of polymers during early stellar evolution. For those that don't know, methane is natural gas, or main component of natural gas, and it has 1 carbon and 3 hydrogens on the outside of it. And the majority of polymers which have methane chained together, those are hydrocarbons. So basically, we have hydrocarbons forming in the high atmospheres of evolving stars without any life present whatsoever. So it throws a wrench in the works. How exactly did natural gas, which is supposedly a fossil fuel, end up in the atmospheres of Jupiter, Saturn, Uranium, and Neptune? I don't see that written anywhere in any online article, because it's basically a complete falsification that you need life to form natural gas and hydrocarbons. They form naturally in the high atmospheres. Speaking of chemoclines, meaning as you go deeper into a star, you'll have different chemicals as well. They'll mix between layers. So some layers will be above others, and some will be below where they're supposed to be. So you'll have different mixing. Unfortunately, a lot of the scientists, they looked at uranium and Neptune and they said, well, here we have a star or a planet that has hydrogen and helium in its atmosphere, and nothing else considerably worth looking at. Unfortunately for them, they were looking at the top atmosphere where the lightest elements are, clearly hydrogen and helium. All you had to do was go into the interior of those objects to find that it gets more interesting. That's where the majority of the methane and the carbon compounds are being formed. So I drew a little graph here. You have a hydrogen, helium on the outside, and you have your methane and carbon compounds forming right below the surface. They would have just sent a probe in there, maybe a high pressure probe. They would have seen that. But back in the 1970s and 80s, that that wasn't exactly in the budget, because just getting a spacecraft there was expensive enough. As well, for those that don't know, I've seen this firsthand because I've been watching a lot of old school videos of interviews of scientists that lived in the 1970s, news programs, things like that are archived online on YouTube. But these scientists, they don't have a formation model of Neptune and Uranus. They just ignore them. They're not really all that important or interesting to them. They're just ice giants. They're out there really far away. There's nothing important to see. They're just remains of the disk, and there's nothing actually happening interesting. But that kind of attitude, brushing two of the most interesting objects in our solar system off as if they're just unimportant, uninteresting, isn't really a good attitude to have. Because instead of metamorphosis, now we have a theory that can explain what's happening in their interior. They're forming new Earths. And we need to adjust our theories to account for that. Meaning they're intermediate aged, they're very, very, very old, and there's a lot of interesting chemistry happening in there. So somehow we need to get to studying those objects in depth to see if this theory can hold water. And sort of a history lesson, the Voyager 2 spacecraft was the only spacecraft to have visited Neptune and Uranium. And that is interesting in itself because we have spacecrafts visiting all over the solar system, yet only one has visited the two outermost objects, except for Pluto, obviously. And that's weird because what it tells you is that not only do we not look at them as being very interesting, but we have very, very little data on them. And the more data we get, the more it will help me out in this theory development and others who are developing this theory as well. But you got to look at these objects. You just can't ignore them. But that's basically what we're ended up doing because money is making it very limiting. As well, the Voyager 2 spacecraft ended its mission after it had passed Neptune on October 2nd, 1989. Literally, I was 3 years old. I was a 3-year-old boy when it passed that object. And I wish I could go back in time and say to my 3-year-old self or 4-year-old self or 5-year-old self, be like, hey, this satellite was going to pass Neptune right now. Well, actually, I was 4 years old. I was 4 years old. And in the future, when you're older, when you're in your 30s and 20s or late 20s, you're going to make a major discovery that's going to explain what that thing is. And it would be just really weird to talk to my, younger self, my little tot self, concerning that. I just thought that was interesting. It's like stretching across my entire life. All these events are stretching across my life. And to look at the past and study history books, and the discoveries were made over hundreds of years, maybe even thousands of years, and was going so slowly. But now it's like just inside of my little life that we're making these discoveries. I think that's incredible. They're rapidly they're increasing. The discovery rate is increasing significantly. Should be interesting over the next couple years to see what happens in astronomy. All right, you guys, take it easy.